Hey guys, today we are going to discuss this problem here, finding the interval of convergence of the following power series. Let's consider first one, right? I think we did this kind of series last week, right? Let's consider this one, first one. Sum goes from 0 to infinity, factorial n squared divided by 2n factorial xn. Alright, let's use the ratio test. From ratio test, a sub n plus 1 and a n, consider the modulus of that, which is same with n plus 1 or factorial of n plus 1, everything squared, right? Everything squared divided by 2n plus 2 factorial, and the other term is an, which is n factorial squared 2n factorial, and here you have, when you simplify this you get mod of x, right? You can simplify further, so when you simplify that further, when you simplify that bit further, mod of a sub n plus 1, a sub n is equal to do you get n plus 1 squared? Here you get 2n plus 2, 2n plus 1 times mod of x, right? Alright, and so obviously this bit here, obviously this bit here goes to 1/4, right, as n tends to infinity, right? So a mod of a sub n plus 1, a sub n goes to 1/4 mod of x as n tends to infinity, right? So from ratio test, so that power series is convergent whenever this bit is less than 1. If this bit is less than 1, that one is convergent, right? Otherwise, if this bit is greater than 1, that is divergent. That power series is divergent, right? So let's consider the convergent axis. So if mod of x is less than 4, that power series is convergent. So now we can consider two cases here. We should consider what happened to the power series when x is equal to -4. We have to check whether it is convergent divergent at x equal to 4. Right, let's check those two cases now. When x equals 4, right, we can show that this bit is we can show that, so we get this series. What do you get? Summation n factorial squared divided by 2n factorial and 4 to the n. Last time we discussed this problem, or if you don't remember, so we can work this out. So 1 plus 1, we consider about binomial expansion of this, right, which is same with 4 to the n, right, and this is the definition of binomial expansion. K goes from 0 to 2n, and 2n ck times 1 to the power k times 1 to the power 2n minus k, right? So this one is so this bit is greater than or equal to one of the terms of the binomial expansion. This is a term of that binomial expansion that should be less than or equal to whole binomial expansion, because these are positive numbers, right? And so here we get 4 to the n greater than, and you simplify that, this one, you simplify this bit, you get 2n factorial n factorial squared. So that means 4 to the n n factorial squared divided by 2n is bigger than 1 for all n, right, for all n. So all terms of this series is bigger than 1. That means that, say, this is a sub n, right? The limit of these terms does not converge to 0 as n goes to infinity. So that means the series is divergent. Similarly, you can show that when x is equal to -1, you can show that the series is divergent. So, alright, therefore the interval of convergence of that power series is -4. 4. Right. Let's consider this example now, right? Sum of sine of 1 over n squared, this power series, n squared times xn. So let's, to find the radius of convergence, we should apply ratio test. So from the ratio test, a n sub n plus 1 divided by a sub n modulus modulus sine of 1 over n of n 1 plus n squared divided by sine of 1 over n squared, everything modulus and mod x, right? So let's find the limit as n tends to infinity, right? So this one here, the limit n goes to infinity, we have to find the limit of this. So here, look at this one here, sine of 1 over n plus 1 squared, sine of 1 over n squared, right? Let's take the limit of this, right? So as n tends to infinity, this bit goes to 0, as well as the bottom function, that bottom one also goes to 0. So definitely you have to use the L'Hopital's rule here. So if your denominator and numerator goes to 0 as x goes to 0, right? So the limit of that rational function is equal to the same with the limit of this one. So alright, let's apply L'Hopital's rule. Cos differentiate sine, you get cos 1 over n plus 1 square. You differentiate this one with respect to n, or let's put x here, right? And differentiation of this one is negative 2 x plus 1 to the minus 3, and the bottom function cos of 1 over x squared and negative 2 times x to the power minus 3. So as x goes to infinity, right, we can show that this bit goes to 1, right? As x tends to infinity, we can show that this bit goes to 1. So from the ratio test, so a sub n plus 1 divided by a sub n goes to modulus of x as n tends to infinity. So that means when modulus of x is less than 1, that power series is convergent. That power series is convergent if x greater than 1. That power series is divergent, right? Now let's consider two cases separately. We know x in between -1 and +1, the power series is convergent. Outside of this pole, the power series is divergent. Now we consider these points separately. When when x is equal to 1, so we get some sine 1 over n squared. I think we showed that this one is convergent. You can show that for all x, any real number, sine of x, mod of sine of x is less than or equal mod of x. From this one, right, then we can prove this property, right? So from this sum of sine of 1 over n squared is less than or equal to 1 over n squared, right? We know that this one is convergent, then this one is convergent. That means sine of 1 over n squared is convergent absolutely, right? Absolutely. Since sine of 1 over n squared is positive, so this one is same with, so this one is same with this. Therefore this series sine of 1 over n squared is convergent. And you can show. So now we consider other case, x equals -1, then you get an alternative series sine 1 over n squared, right? So here this is an alternative series. So sine function, this is the sine function, so which is a decreasing function in the considered decreasing function. It is decreasing to 0, right? Decreasing function, and this series is an alternative. Therefore this power series, this series is convergent. So we can conclude that above power series, that one sine of 1 over n squared x n is convergent in this interval.